Okay, so in this video, we're going to cover both scientific notation and the units of measurement, but it's all on page 13, and it's really not that much writing, but scientific notation is something that's going to come up a little bit on and off throughout the year, so I want to make sure you get this. So we might spend a little more time on that top half than the bottom half, but should not take too long. So what is scientific notation, really? Well, it's just a way of writing numbers that are either too big or too small to be easily written in standard form. Or, in our case, it's a special way of getting rid of significant figures sometimes when we just don't have a way of keeping some zeros significant without others. So, sometimes we're going to use it for sig fig reasons, but really, it's a scientist's way of being lazy, so they don't have to write out all those zeros or count all those zeros every single time they're trying to talk and compare measurements. So it's generally going to be written in this standard form, a times x to the b. And a is what we call the coefficient or the base of this scientific notation number. It's all one number, but this is the base part of the number, the part before the times 10. And then the b is just the exponent that the 10 is raised to. So it can be a positive or a negative number, and we're going to talk about when it is each, but we just have to make sure we know those specific parts of our scientific notation numbers. And I have that still up at the top for reference, but let's talk about how do we take a number and put it into scientific notation, put it into this form. And the first step is paying attention to the decimal. We're going to move the decimal from wherever it is, either invisible at the end of the number or written someplace in the middle of that number. And we're going to move it and put it after the first non-zero digit. Now, that's important. There's other types of notation where the decimal can be in different places, but in order to be proper scientific notation, which is what we expect from you in this science class, is that the decimal's after the first non-zero digit. And that is going to create this base for us. We're going to get rid of all of the zeros that are not significant figures. Only sig figs are going to stay in that base. And then we're going to add the times 10 part after it and move on to thinking about and figuring out, well, what is our exponent? And in order to figure out what the exponent is, we actually need to count how many times the decimal moved to get from where it started into this new place that we put it in this base of our scientific notation. So we're going to count how many times it moves and write that number from step 2 that we counted up on the 10 as its exponent and check the sign. If the original number is larger than 1, then that exponent will be positive because it's bigger, it's plus than 1. If the original number is a decimal smaller than 1, like 0.5 or 0.05 or 0.00153, any of those numbers will have a negative exponent because they are smaller than, less than 1. So that's how I remember it. I know there are some fun, interesting sayings or tricks on how to remember moving it left versus right for whether it's positive or negative, but I always found those confusing because you're moving it left to go into scientific notation, but sometimes we ask you to turn things out of scientific notation into standard form, and then the rule is backwards. So my rule always works, and we're going to practice it both ways here in just a moment. So have those simplified kind of original rules shoved up there at the top, and let's try first putting things into scientific notation. And I'm just going to focus on these first 3 examples, and I'm going to have you do these last 3 examples on your own. Try those and check your own work. So, on these examples, let's start by putting the decimal after the first non-zero digit. So, in this 3 million, 3 million, the first non-zero digit that I get to, going left to right, is this 3. So I'm going to put the decimal there, and then I'm going to start paying attention to the significant figures. Well, since there's no decimal, that 3 is the only significant figures. All of these zeros are trailing zeros, and there was not a decimal written here at the end of the number, but that's where it's understood to be if there is no decimal written. So it's invisible, which means these zeros are not sig figs. So I'm going to bring my 3, and you can write the decimal or not here because it's just one number. It doesn't really matter. Once again, it's understood to be at the end of the number if there's just none written. But I'll go ahead and write it, and then put my times 10. And now I just need to figure out what that exponent is going to be. And I'm going to count how many times my decimal had to move in order to get from where it was starting to where I now put it, and that is 6 times. So I know this number is going to be a 6 up here. And then I look at my original number and go, yeah, that's a lot bigger than 1. So that is going to be a positive 6. We don't have to write the plus sign, but it is not going to be negative. So that is our answer. Now technically, if that was meters per second before, we can add that meters per second label to it. Still the same measurement, still the same number, just less zeros that weren't significant to begin with, so why even write them? If we go across to this next number, I'm looking at the first non-zero digit moving left to right, and that is the 1. So I have to put my decimal after that first non-zero digit, and the only sig figs that we had here was this 1.2. None of those leading zeros were significant. So it's going to be 1.2 times 10, and then I have to count how many times my decimal, which I do see here, got moved to be where it is now. And the answer is 7. So my exponent is going to be a 7, but here, because this number was a decimal, it was smaller than 1, this is in fact a negative 7 exponent on there. And then, of course, the units that are just along for the ride at this point, those aren't changing because we're just changing the way the number looks. Everything is the same about the value, just looks a little different. So, one last example together before you do your part. So I'm going to put my decimal after the first non-zero digit, and this time we are going to keep a couple of zeros. All of this is going to be our base because the sandwich 0 is of course significant, and this trailing 0 is significant because there's a decimal written in the number. These leading zeros are not significant though, so just going to keep the 6030 as our base. Do times 10, and then figuring out what my exponent is, 1, 2, 3. And this was smaller than 1, so that should be a negative 3. And then units along for the ride. So hopefully that's not too scary. I know the numbers are not necessarily our favorite, but especially when we got all these zeros, it does do us a favor, and it is worth learning in order to help us out with some of the calculations we'll do in the future. So now don't forget to do these 3 examples so that you can get your stamp, and we'll go ahead and move on to doing the opposite direction. Now here we don't really have any directions for you, so maybe if you need reminders of what you're doing, you can, but because this is kind of going to be the opposite of what we just did to form the scientific notation, because we're going to start by looking at the exponent. That's going to tell us how many times to move the decimal, and we're going to have a decimal here, and so we're going to be moving this decimal 5 times, and because this is a positive 5 exponent, we're going to move the decimal whichever direction it needs to go to make our number larger. So if we start with that base, 1.86, and I'm just moving mine out because I have like half a centimeter until the edge of my page, you guys have a little bit more space. But if I started trying to move this decimal to the left 5 spaces, and thinking about the number I would be making, this would be smaller than 1. So that's not what we're wanting. So we're going to move the decimal the other direction. 1, 2, 3, 4, 5. And these first 2 spaces hopefully are pretty normal, but these last 3, we're moving it past nothing. But remember, we have to move it 5 spaces, and the reason was originally to get rid of zeros that weren't significant. So now we are going to add those zeros back in to let us move that decimal where it's at. And technically, since those weren't sig figs, we shouldn't physically write this decimal, or else it would make it look like I have more sig figs than what we started with. And the purpose isn't to change the number or its precision, just the way it looks. So 186,000 should be written like that this time, instead of like this in scientific notation. And then, of course, meters per second. And then this next one, I'm going to be moving my decimal 7 times, and because of that negative sign there, I'm going to be moving it 7 times in the direction that's going to make it smaller, which is to the left. So 1, 2, 3, 4, 5, 6, 7, and then filling in all 6 of these spaces with zeros. And this time we are going to have to leave this decimal here, just because otherwise it's a different number. And don't worry, even with that decimal there, these 6 zeros are not significant figures. So we can do this, and this is the exact same number of sig figs as the original value had in scientific notation, just a few extra zeros for whatever reason. And if you really like to, like I do, because it helps me actually find that decimal point, sometimes I lose it, I put another 0 in front of that as well. That one is completely optional. I'm not going to judge you either way, whether you write that. So now you do this one last one, and we'll go ahead and point out that this one is a positive exponent, so it's going to be a little more like the first example that we saw than the second one. But give it a try, show me that you've tried it, and I'll get you your stamp when I see you again. And down here at the bottom of the page, we're just going to finish out with a real quick discussion of units. Those things that we put on these numbers to help them mean something. It's not just 5 or 5 million somethings, not 5 million cows, it's 5 million joules or 5 million seconds. All of that is important. So we use the International System of Units in science classes. This is a worldwide standard based on the metric system, which I know is not normal people, everyday units walking around, but it's important that we have a standard system, or else everyone seems to be talking different languages to each other, and in science that can cause problems and mistakes and even deaths. So for the sake of science, we use these common measurements that the rest of the world does. And there's actually 2 different types of units. Base units are units that can be directly measured, like length, time, mass, temperature, something that you can put your hands on a measuring device and hold up to something and measure it, or just hold in your hands and make that measurement. A derived unit, on the other hand, is a quantity that can't be measured directly. It's the opposite of a base unit. These have to be calculated from base units, so they have to be calculated from other measurements. They're not measured directly. This is like volume or area or density. Area is a great example because while you can measure your length and your width of like a rectangle, for example, you're going to have to multiply the length and the width together in order to find that area. You might say, oh no, but I could take a square out that I've already measured the length and the width of. I know its area, and then I can use that to count other things' areas and might put it on the ground and measure how much area it has. But still, you're basing that area measurement off of the original length and width measurements that you made. It's all derived from that length and that width. And volume is one that people sometimes don't realize, because we do have like graduated cylinders to measure volume and stuff with directly, but guess how we figured out where those markings go on the graduated cylinders? From length measurements and diameters of those graduated cylinders that are very carefully created cylinders. So all of those volume measurements are derived measurements, derived units from other base units. So to finish out this page, let's just go over the primary units that you're going to be seeing. Time is going to be seconds. Length is meters, not feet and inches. Mass is going to be grams for our scale of things. For bigger scales, the kilogram is the standard. For liquids volume, which is most of what we're doing, we're going to be using liters or milliliters more for our scale. but a lot of liters in our calculations. Solids are cubic meters. The amount of substances, if I'm talking about how much salt we need for a reaction, we're going to measure that in moles. And then temperature is generally Celsius, but in a few circumstances, it is going to have to be Kelvin. And we'll learn about Kelvin, how it's special when we need it and use it. So that's it. Hope that wasn't too bad. See you in class again next time.